Math 13 students, hello. I have here a discussion on the material in section 6.3. We're going to be talking about estimators and sampling distributions. We will also introduce a new metric, the sample and population proportion. So let me go ahead and share my screen and we'll get going. All right, so section 6.3, estimators and sampling distributions. We have some examples for you and a little bit of theory. All right, so in terms of an outline, we're going to define the notion and the role of an estimator. We'll explore some very basic sampling distribution, and we'll introduce sample and population proportion metrics towards the end. All right, so definitions first. Now, if you've already looked at the material for 6.3, this should be reviewed. You'll remember that an estimator is a sample statistic that is used to approximate or to guess at a population parameter. This is like using your X bar from a smallish sort of sample to approximate mu for a large population. Remember, populations are large. We can't measure them directly. The only thing we can do is take a small little piece, a sample, and measure that, and then try to extrapolate out from that small sample to the larger population. Needless to say, you might be right, you might be wrong. Ideally, when we do this, we would like an unbiased estimator. That just means the sampling distribution does a good job of approximating the true population mean in some fashion or other. And while it's important that the estimator used is unbiased, pretty much every estimator has at least some inherent bias built into it. However, if we acknowledge and adjust for these sorts of things in the language of statistics, we'll go ahead and use these estimators all the time. So here's our first example. Here's a small population. I have no idea what we're measuring, but it's a very, very small population. There's only 5 items, people, objects, whatever, in this population. Now we're going to take a sample of size n equals 4. So really only one of the numbers is going to get left out of the mix. However, we want to consider all possible samples of size n equals 4. So I might end up with the 1, the 2, and the 7. Maybe the 8 doesn't show. Maybe the 7 doesn't show. Yeah, maybe the 2 doesn't show. Maybe the first one doesn't show. Maybe the second number 1 doesn't show. Here's my problem. If we random sample, I don't know which one of those samples I'm going to get. If we do it correctly, the chance of getting any one of those is all about the same, about 1 in 5, because I see 5 possible samples there. So we want to consider all possible samples, and then what we'll do is we're going to find the sample means. So it's relatively straightforward. It's relatively easy to do. 1 plus 1 plus 2 plus 7. Add that together, then you're going to divide the result by 4. And you get the 2.75. So the arithmetic is really not very intense here at all, adding up 4 numbers and dividing by 4. But I want to do that for all of those samples. Now, I'm not going to make you watch me do it for all of the samples, but if I did do that, you get these numbers here. And you'll notice that they vary quite a bit, from the low of 2.75 to a high of 4.5, almost a factor of 2 there. Now, what about the actual population mean? Well, if we add those 5 numbers up and divide by 5, we'll get mu equals 3.8. Notice the change in the notation also. Mu is a parameter. It speaks to an entire population. The whole point of this example is to note that the sample I get is random in terms of which one it is, and it's highly unlikely that my sample is going to exactly match the population mean. After all, I've left out some of the data. How could it be exact? If it was, it'd probably be a coincidence, I would think. So the actual population mean is 3.8. And you'll note that some of those sample means are close. Some of them are far, if you will, from the true population mean. Probability says we're going to get one, but which one? And really, in some sense, this is really the focal point of the probability topic. We really want to be able to address probability when we sample. That's really where it's going to be key. So if I take all of those sample means, put them all together, I get what we call a sampling distribution, at least for the mean in that first example there. What was the commonality there? The sample size was the same in every case, and we looked at all possible samples of a given size. And it's important to keep that in mind. This can really mean a lot of samples in terms of the theory that we will be addressing soon enough in section 6.4. Let me give you a quick example. Suppose we've got a population of size n equals 20. And we're going to take a sample of size n equals 10, little n. So the order I pick these numbers does not matter when it comes to calculating the mean. You add them up and addition is commutative. So if I take a sample of size 10 from a population of size 20, there are almost 185,000 possible samples that I might get. I'll get just one, but one of 185,000 different ones. And that's going to become important and significant. By the way, that number, 185,000 give or take, that comes right out of choosing R of n objects when order does not matter. That's a combination from 4.4 in previous chapter or two. Now, I want to save the last little bit of this presentation for introducing a new metric. A sample proportion is the proportion of a sample that has some particular characteristic. The sample proportion is usually a fraction in definition, a decimal in statement, but sometimes that decimal will be converted to a percentage. Now, a population proportion is just the proportion of a population that has some particular characteristics. So we see first the sample proportion and then the population proportion, the sample statistic and the population parameter. Notation. We let X be the number of items in the sample of the population and has some of this well-defined characteristic, whatever it might be. So your sample proportion, p hat, as we like to say, is equal to x over n. And that's exactly how we call it. We call it p hat. P hat, it's fun to say. Now, for a population proportion, the formula is identical in pretty much every regard, but we drop the little hat on the p because we have a population parameter here. So p is equal to x divided by, you'll notice the large uppercase N, right? That's your sample size. Here's a very quick example. We have a sample of 234 students, 175 of them said they planned on taking stats this semester. A little late to start. We want to find the sample proportion of students planning on taking statistics. So we had 175, so let me come back over here to Mr. Calculator. 175, we'll divide that by 234. So 175 divided by 234, 0.7478 and change, bringing it back over here, rounding to 3 decimal places, 0.748. I usually choose a 3 decimal place rounding rule here, but there is no real hard and fast rounding rule. And we don't ding you, we actually ask you to round to a particular level of accuracy. So your sample proportion, 0.748. Right now, that's the best guess you have for all students everywhere who plan on taking stats this semester, or about 70, almost 75%. So a little bit of a summary. We've defined the role of an estimator. You have a good idea now of what we're going to use that to do. We're going to use it to guess at a population parameter. We've taken a look at the sampling distribution notion, which comes directly from all those samples that we might possibly get. And then I took a little bit of time to introduce the sample and population proportion metrics. So that's really the end of this particular detail. I will note that 6.3 and 6.4 is where the theory that we use for the balance of the semester comes out and plays. It's an advanced theory. It's usually quite difficult for students to apprehend or understand in an intuitive fashion. That's okay, because the actual utility of it is really pretty straightforward, and students don't have too much of a problem actually using the theory. It's really built into your calculator, and it comes down to comparison of different numbers. So that brings me to the end of my presentation. I'll stop my sharing now, and I'll say goodbye, and I'll say come on back after you've looked at some problems, and visit me during my office hours, and we'll get your calculator to work correctly.